Welcome to Brain Vision.
Okay, in this question, we have a wheel that's spinning, initially at position theta equals 0 at time t equals 0. It has an angular acceleration alpha of 2 times the time, so the angular acceleration is increasing with time. The radius is 200 millimeters, which we can rewrite as simply 0.2 meters. The initial velocity, angular velocity, is 0.1 radians per second. And we want to find the linear velocity and acceleration of point A after these 2 seconds. So to do that, we need to find a formula for theta. So the actual position after these 2 seconds, we can do that pretty simply, just using our angular kinematics. So theta will equal the initial position, which is just 0, plus that initial angular velocity times the time, plus 1/2 times the angular acceleration times the time squared. So if we put all of that into a calculator, so quick correction actually here. Instead of being the equation shown, we're going to have to use a little bit of calculus because this is only good for a constant acceleration. So instead of this, we actually are going to have to do a little integral. So to start with, we say, well, the angular acceleration just simply equals 2t. If we integrate the angular acceleration, we get the angular velocity, which will give us 1 times t squared plus that initial angular velocity. If we integrate this again, we'll get the position, which will then be 1/3 t cubed plus that initial angular velocity times the time plus our initial position, which is just 0. So we can go ahead and figure out what our angular acceleration is at time t equals 2, what our angular velocity is, and what our angular position is. So the angular velocity will simply be 4 radians per second squared at time t equals 2. Our angular velocity will be 1 times 2 squared, so that's 4, plus the initial angular velocity, which was just 0.1, so this will be 4.1 radians per second, and our position will be 1/3 t cubed, which will be 8/3 plus 0.1 times 2, so plus 0.2, or about 2.87 radians. Okay, at this point then, we can go ahead and figure out what our linear velocities and acceleration are at that point. And we just use a typical formula here where we use the radius times omega times the cosine of the position I hat plus the sine of the position j hat. And we do the same thing for the angular acceleration, for the linear acceleration. Let me rewrite that here quick. Except we'll have the radius times the angular acceleration, and then times the cosine of theta I hat plus the sine of theta j hat. And one quick correction here, I messed up the I hats and the j hats, and we need to be very careful with these. So I just wanted to double check that. But we noticed that at theta equals 0, a cosine of 0 would give, would give 1, and we're only moving in the vertical direction at that point. So cosine here must be associated with the j hat term. And then we also notice that as we rotate then, that decreases until you get to 0. But up at the top, at 90 degrees or pi over 2 radians, the velocity and the acceleration will only be to the left. So the signs then will only be in the I hat direction, but they'll actually end up being in the negative I hat direction. So I need to make sure I include a negative sign here in order to be complete. And once we put those numbers in, we get that 2.87 radians, which is a little bit less than half a full rotation. So that'll be over here on the left. So what we should expect then is the velocity and the acceleration in both the x and the y directions to be negative here. Okay, and then the answers we get here for the velocity are negative 0.214 I hat minus 0.770 J hat. I'm sorry, I actually wrote this in the wrong position here. This is the velocity here. Or this is the acceleration here that I just wrote. So this is in meters per second squared. So sorry for the crossed lines here, but the velocity is then negative 0.790. I wrote the j hat first again, sorry. Negative 0.220 I hat minus 0.790 j hat. That's in meters per second. And those are our linear velocity and accelerations of point A.